Okay, so let's resume. So I have been asked to speak about structures a little bit. So you have already encountered many structures during this workshop. So and the point of my talk is really today to explain a little bit how Lean really handles structure and how you can define your own structure, how can you define terms inside structures and so on. Again, this is just probably a way of putting together knowledge that you have already acquired or to which you have already been confronted. So the first point I really want to, so all these will be pulled to the repository, and there are exercises as well. They will be pushed actually as soon as I finish my lecture. But one point I wanted to stress is that there is this very, well, this book, I wasn't going to say very beautiful. It is a beautiful book. It is terse from time to time, so it's not very easy to read, but in particular in this section, there is a whole discussion of what structures are. It is really written, I would say, from an audience of perhaps computer scientists or more than the mathematicians. So it's perhaps not a very easy read at the first try, but at any rate, it's a good reference. Okay, so let's start. So the first thing, when you want to define a structure, we will see exactly what the structure is. But for the time being, the idea of a structure is that of a mathematical structure. The Gaussian integers are a mathematical structure. A differential manifold is a mathematical structure. A group is a mathematical structure. And of course, you want at a certain point to be able to speak about hierarchies of mathematical structures. So the ring also has a group structure on it, additive stuff, and so on. And so the idea is that all these things can be built together quite nicely. But at any rate, the first thing you want to do when you define a structure is, well, you write structure, then you give it a name, and then you give a list of fields.
So is structure a type?
Oh, is structure a type? Structure is a way of defining a type. So structure by itself is a command that instructs Lean that what follows is defining a type. I'm now going to dwell a little bit in the details of what all these things mean, why are they colon, and what's the relationship between type and structure and so on. But if at the end of my explanation it's still not clear, please ask the question again. Okay.
Sorry, can I ask another question? So when I was explaining like topological spaces, I had class instead of structure.
Yeah, this will come at the very end of my talk. Yes, I should say that the end of my talk will be there are a special kind of structures that are called classes, and you can very much mess things while using classes, and I will show a problem while using classes, and Thomas' talk, which follows mine, will precisely try to explain how we can fix the problem that I will point out at the end. But so I will also mention classes and the relationship between structures and classes. Yeah, so so how should you read these? So you basically have this structure is just something like lemma or def or abbreviation. So okay, so it's just a way, an instruction to Lean to say, okay, what follows is a collection of things, and I'm going to tell you what these things are, and then all together construct my structure. Like instead of my structure, you will soon have. Of course, there will be plenty of examples, and so this is just an overall view on this. Okay, so some points, and then we pass to the examples. Yeah, okay, I have the examples. Okay. So these, as you see from these ideas, the point is that each line is a term of a certain type. This is the usual syntax we have already encountered, which when you have something colon something else, the thing on the right is a type and the thing on the left is a term. So basically you are saying a structure is a way of bundling together several terms coming from these types. And it is really a collection of things like this. So typically, what happens? Well, sometimes, not always, sometimes some of these types on the right are living prop. So they are themselves statements. And so to say that, for instance, suppose the first type is improp, first type can be a proof, a statement that some equality holds. Then to declare first field colon first type means that you're giving yourself a proof that a certain condition is met. So the way you can use structure to impose, for instance, and this will be an example, associativity on a certain operation, is that, well, you give yourself the operation and then you say, oh, I want among my several fields to have a proof that this operation is associative. Associative will be a prop, and so giving yourself this proof of the associativity will be a way to guarantee or to impose on your structure that this operation is associative. And likewise for commutativity or I don't know what you have seen in whose lecture, I think in Alex's lecture about filters, you want to say that, oh, filters are closed with respect to taking subsets, for instance. Okay, then this is a proposition, the fact that they are closed, and then you are requiring that you have a proof of this. Now, going closer to the question that has just been asked. So when you define a structure, Lean automatically constructs a term which is automatically called the name of your structure .mk for make, and which, as everything, is a term of some type. And let's try to inspect the type of this my structure .make. Its type is an arrow type, a very long arrow type, that goes from the first type to the second type to the third type to the last type, and then to my structure. So this shows you that my structure is indeed a type. And this tells you how you can construct terms of these types. Because this tells you that once you want to produce a term in my structure, what you have to give yourself is a term in the first type, then a term in the second type, then a third in the third type, and so on, then a third in the last type. And this thing here is a huge function that applied to all these arguments produces a term in my structure. Okay? So from the type theoretical point of view, this is certainly a type whose terms can be constructed in these ways. Okay? Not only these, but you have something more. You have given a structure, you can project a term of this form to any of these component type, because at the end of the day, this, as I was saying, is a bundle, a structure, each term of which is well, has that many fields. Each of these component belongs to some type, and so you can project a term of this structure to, for instance, the last type, by taking a term, which is a collection of all these things, and forgetting everything but the last field. And this is also automatically constructed by Lee. Now there is a small detail about X, which I don't want to speak about. And these also. So let me immediately move to the examples. For some reason, the examples I'm seeing here, well, it doesn't matter. I had changed, I suppose, my lecture, but it doesn't matter. Okay, let me move to the example that can be perhaps more instructive. So first of all, let's, is it large enough? Perhaps I have to make not large enough. Good, larger, fine, like this, okay, good. Okay, this quadratic algebra. So this quadratic algebra is the thing that Antoine discussed this morning, I suppose. So his idea was, okay, I take R, which is a ring. I take two elements in the ring, and he wanted to construct a quadratic algebra obtained by adjoining the roots of x squared plus ax plus b to R. And he said, well, I defined this just as a structure, so of pair of elements in R. So the idea, think of the Gaussian integer or just the complex numbers as an R algebra. So what he's basically A and B are the real and imaginary part of a complex number. And what he is saying is that a quadratic algebra is just a structure composed of two elements. Both of these terms belong to R. And then, of course, you will need, I won't do it here, but it was part of his lecture. He wants to put a group structure, a ring structure. And then, of course, the group and the ring structure will tell you how X and Y interact. But on its own, this structure, so the terms of this structure are just pairs. And this is what this says.
So is the structure the product of all these types?
Is it a product of all these?
Like product in the sense of
like a pi type?
Yeah.
Yes, I think.
Some can depend on others.
Yeah, exactly. It's a well. This doesn't. It's a dependent.
It's still a pi type, but it's not a product.
Oh yes, yes. It's a pi type. It's not a product. In the sense, so the problem is that so it's dependent product.
Oh.
In the sense that so. Well, we'll see an example below. I'll try to when I come to the associativity. I hope to remember to discuss these, but if not, tell me something on this. What do they want to say? Yes. So, of course, there is the point that, so let's say, from the user perspective, structures are all very nice, but you immediately forget what you declared because, well, you give names to things, and then when you write your code, you have very well in mind what you're doing, and then 2 days later you forgot either the structure of this thing, or you forgot how you defined it, or perhaps you're trying to work with a structure that has been defined by someone else. And so there are a couple of subtleties that I will try to emphasize that are often useful when when defining and playing and working with structures. One is this comment, which is called what's new. Let me comment this for the time being. What's new? Well, it does what it says. It tells you what is new after declaring this structure. So if I write what's new right before structure, on the right-hand side, I have a list of all the things that have already automatically been created by Lean once you say when you declare a new structure. So some of them are not terribly interesting, but one that I'd like to stress, for instance, is this one. So the two terms, they're called X and Y, and they're both terms in R. Now, automatically, Lean creates this definition, which is quadratic algebra dot X, whose type is an arrow from R to a pair AB in R to a term in quadratic algebra to R. Let's try to parse the type of this gadget.
What is the U1 doing?
Oh, the U1 is just because so as we said, everything lives in a certain universe. I've not fixed a universe level for R. If I had defined quadratic algebra only for rings in level 37, then there will not be this U1. What this U1 here means is that indeed you have a collection of definitions, one for each universe level. And if you are in level U1, where U1 is just a variable for a universe level, then this is the corresponding definitions that we are having. And so its term, the type of this dot X is RAB, quadratic algebra AB R. What does it mean? Well, it means that if each time you give yourself a type R, which is supposed to be a ring, but to define these, you don't actually need it R be a ring. You give yourself R, then you give the two elements A and B in R, and you give yourself a term in the quadratic algebra attached to R defined by A and B. These function provides an element in R. Or in other words, another way of saying it is that you forget R I say, well, for each a and b, I have the x coordinate function, which is a function going from the quadratic algebra attached to a and b to R. This is what a coordinate function does, right? It's really the first projection. So in other words, this means that now if you take a term in quadratic algebra, which will be a pair of things, this is a function that takes this pair and gives you the first term back. So what I'm trying to stress here is that automatically Lean uses, and this is very this is like what we do in geometry, in algebraic or differential geometry. Once you have the name of the components, you can also look at the names of these components as being functions, as being projections from the structures down to R. This is what it's simply what it's doing. Let's make some other examples. Has zero. What is this? Has zero. If you write structure has zero x type, I'm basically defining a pointed type, because I'm just declaring that for every type capital X, I want to consider the structure of endowing X with a zero, which is just, well, picking an element in X. This A0 is just an element in X. Of course, someone can complain, should complain perhaps, that if I call it zero, it better be related to additive or multiplicative or to some operations, because otherwise, why am I calling it 0 and not 37, or why I'm not calling it a point or a star? This will come later, and this will certainly come later also in this file, but this is very much related to the way, and this Thomas will speak about it, we create hierarchies is by first just providing types with the relevant objects, and then by providing properties relating these objects. So we start just by giving it 0. Then another thing, I will discuss this notation in a while. Another thing you can do is say I define a magma to be what? Well, to be just a set with an operation, binary operation. Everything here is completely unrelated to any, for the time being, to any mathematical content in a sense. This is just a function saying that you're declaring a magma just means that you are giving your type, giving yourself a binary operation. Yes.
So you've defined magma and has 0. Could
Yep.
you kind of like, if we have like a list of theorems for things with magmas, a list of theorems for things that has 0, could you have like a structure that's like both a magma and has 0, and it imports all of these?
Line 41.
Line 41. Line 41 is a way of saying, okay, nice. Now I have a structure of a 0, I have a structure of a magma, but on their own, they are not terribly interesting. Perhaps what is more interesting is to combine these structures together. And this is exactly what this extends command does. But before going, and I will certainly go to that in a second, I first of all want to have a look again to go back to our type theory class we had this morning, because well, it's a personal advice, but it's something that I find it very useful when you try to dig into how Lean does things. Keep on asking yourself, what is the type of this gadget? You see something, it will certainly have a type, because everything has a type. And if you cannot immediately spot what the type of something is perhaps because there's something, well, there is room for reflection, and then it's good to and then you can just spend 3 minutes trying to understand, okay, what is this? So magma.sum, for instance, what is it? Why does it make sense? Where should it leave? Is the function, for instance, is it the term on its own? Let's expect, and you can have the answer is there, of course. So first of all, this already shows you some on its own. It might be a very general umbrella term that can occur in many structures. So this is why, in general, Lean always prepends the name of the structure to your to the object you're declaring. Okay, so that if I come up with something else that also has a sum field, that will not be mixed up. And then these, let's see, well, it's a function that takes a type, then takes this self magma x. This is a term that is a term in magma of x. So basically, this is the term witnessing that x is endowed with a magma structure. Because otherwise, these will not be defined a priori. Sum is only defined when x is a magma. So once you have a type, so x is of type, and a term that witnesses the existence of a magma structure on x, well, magma.sum is your binary relation on x. So from x.
Is self a keyword that just extracts?
Say it again.
Is self a keyword in Lean that extracts?
It's more than a keyword. Is an automatically generated name for the variable. It is saying this makes sense only in a context where x is a type, and when there exists a term of magma on that type. Okay, so but I should give it a name. So this is just in a sense an anonymous name given to the variable representing the term in this structure. Okay. Another thing you can do when you have a structure is print. Print is very useful when you have structures with many variables. For instance, what is a topological manifold in Lean? You can ask this thing yourself and print. Don't do it; it will be very scary. But okay, let's say what is topological space? Let's do mildly. Print a structure. It tells you how it has been defined. Of course, you can also right-click, go to the documentation, something, but it's something you can do in a file. So if you do it for magma, it tells us, well, it is a structure. It has just one parameter, which is the type x. So this parameter is x, and it has this field, which is the sum. It only has one field, which is the sum, and it has one constructor. In other words, in order, this constructor is very important. It tells you how to produce terms in magma. And once more, let's try to have a look at the typing of constructor. It tells you that each time you have a type x, and each time that you give yourself a binary function on x, well, you have actually produced a magma structure on this x. Okay, monoid. And this was the question I've received. One thing that makes sense, and of course you want to make, is to build more and more complicated structures starting from easiest one. So a monoid will be, for me here, a magma with a 0. Yes, the problem is, if you remember, I insisted that 0 was just a name so far that I have given to a point in my x. So if we really want to, I could do this, of course. I could forget these two lines. And Lean will not complain. I mean, Lean, so far Lean is concerned, I can define everything with any name I so wish. But if I do this, I will certainly have a pointed type together with a binary operation that is associative. But this point, although I called it 0, it will not be a 0. It will have no relationship with the sum. So if I want to define a monoid, I want to say that my 0 is actually 0 on the right and on the left, and to say that the sum is associative. So now, now I can do it again. Print. Where is my here? Print monoid, and you will see that it does many fields. 1, 2, 3, 4, 5 fields, although there are just 3 years. And this is exactly the power of extends. What extends does is that it first looks at all the fields that come with the first and the second, and then add to these fields these three. So in particular, one thing that one could also do is extend the structure with no field at all. Because since you are extending two structures, this is a way of just bundling these two. In this way, there will certainly not be a monoid, but it will be a pointed set with a binary operation and nothing else. But this, so this extend is extremely powerful because it allows you to extend already defined things. Okay, let me, other questions so far?
What happens if you comment out three properties and just print monoid?
If I print monoid, I just have two fields, which are the two fields coming from 0 and 1. So one is the 0 and the other is the binary operation. And there's nothing more. Okay? Okay. Now, other questions? Yep.
So if you're adding has 0x, would have 0x check whether this function could have a combination with other function to generate a new field or something. Like if you had 0 and also you can do some 0, maybe we have some other proposition we could state. Like would that be automatically checking?
I'm not sure to understand the example. So the answer, as a rule of thumb, I would say no, because it doesn't do much automatically. But this is not a good answer. So perhaps you have in mind an example of. So you're saying if.
Like we have 3 and now we're printing, we have 5. Does that too come from like?
These two, they come from the fact that.
Would it be possible to have 6? We're saying like 3.
Magma comes with 1.
Mm-hmm.
Some 0 has 0 has 1 0.
So we would not like adding something more like that we already stated.
Well, you can, for instance, also decide that every monoid has to be a topological space. Why not? So I can say, okay, a monoid for me is a topological space with a 0, with a binary operation, and such that this combined thing. I could, why not? And then if I print monoid,
you could say topological monoid and the continuity.
Yeah, exactly. I agree, but I don't want to. And then now, how many fields do I have? I have what are the opens? What are the properties of the topology? So 1, 2, 3, 4, 5, 6, 7, 8, 9 fields now. And if I can decide that it's also a differential manifold, and then there are 79. Okay, you can do as much as your fingers can type. You can keep on adding. Okay. Does that answer your question? Great. Okay, so now that we have structures, we want to produce terms in these things, and we have already seen. And now I will not take too much time speaking about this. Just to, especially if you want to look at Mathlib or look at the library or look at material produced by other people, just to show you that there are several ways of defining terms that are all equivalent, but they're different syntaxes, and they sometimes show off. And you have already seen someone asked a question to Heather a couple of days ago, and oh no, she changed the syntax, but without changing the content. So let's see, for instance, 4 ways of defining the same object in the quadratic algebra attached to numbers 37, 42 over Z. So first of all, let's observe that lean can be of some use. So when you say, oh, I want to, so remember the quadratic algebra is something taking the 37 and 42. So this is basically adding the square roots of x squared plus 37x plus 42 to Z. And now you want to define something, you forgot what it is. So you can do colon equal. This is something that either already explained to you. If you do colon equal, you have an underscore, then you have this bulb, generate a skeleton for the structure, and then you have x, y. And then you can say, okay, for x I take -1, and for y I take 1, for instance. Another way of doing it is by immediately declaring colon equal, and you say, okay, x is -1, y is 1. This is another way of defining a term in this structure. Another thing, this is very close to what you have used for the if and only if or the and constructor. Because these funny brackets here, they are in a sense stricter than these ones, because in these ones you can swap, since you are providing the labeling of the fields explicitly, you can also swap them without changing the value of the type. So I can also define beta prime to be x equals -1 and y equals 1. This would be the same. These two things are the same, because really the labeling is conserved. This is a different object. This is a different constructor. So you let lean knows that this is the first field and this is the second field. And otherwise, you can also enter static mode. You say by, and then lean asks you to produce a term in this quadratic algebra, and we have seen that there is this tactic, which is done on purpose, which is the constructor tactic. And once you apply the constructor tactic, Leans observed that that this has two constructors, and so you have to produce a term in Z and another term in Z, and then you say for the first one I want to use -1, and for the second one I want to use 1. And now if you try to check if these things are equal, the answer is yes, and they're equal by definition. Refl closes this thing. So the first, the second, the third, and the fourth definition are all the same. So you're basically free to choose the one you prefer. Okay, so this covers a little bit the way, all this is very compact. There are exercises after all, but these are ways of defining terms, explicit terms in explicit types. By explicit type, I mean this, the quadratic algebra for 37, 42. This is an explicit, you have chosen 37, you have chosen 42, you have this explicit structure, you want to produce an explicit element there, for instance, -1, 1. But there are another things you can do is to say, okay, I've defined the idea of a monoid or of a magma, and later of perhaps a topological space, and now I want to show that N or R or the Hamiltonian or whatever has this structure, in the sense that can be endowed with the structure of a group, can be endowed with the structure of a ring, can be endowed with the structure of topological space. And this is done in a sense in the same way, and this is not completely absurd. These are let's try to go back to what monoid was. Monoid was a way of bundling structures on X, in the same way as quadratic algebra was a way of bundling two terms of R in a certain way. So really, the fact that you're bundling stuff allows you at the same time to define very explicit very explicit types, or really encoding the idea a certain type can be endowed with a certain structure or mathematical structure. So let's see, for instance, how you can how can you convince Lean that there is a 0 on N? Well, I have to give to Lean for the field 0 prime an element of N. Of course, I can use 0, and this would be happy. I can also use 101. This will be equally happy. So far, I'm not asking anything, so I can decide that my point in N is whatever I want. Bool. I can put a 0 in bool. What do you want to use? Well, you have not so many choices. You have two choices. So either use true or false. Let's use true. Why not? These I will discuss this later on, perhaps. Okay, now I want to put and so on. So, and this is the way you build things in general. You want to define a magma structure on N. I'm suggesting that you use the addition that has already been defined. But there is one important thing that I'd like to stress here, that the fact that I'm here able to use this symbol means that, or perhaps I should say something better. Let me.
So why are you allowed to use just use and something? Is it just because has zero has only one field?
Yeah, exactly. If you want, I can do constructor. It would be the same.
Oh, I see.
I can add this constructor, but it doesn't change anything. Okay, and this also equal us saying. All the same. Okay. So suppose now that you have defined this addition the usual way with by induction on and then you define this binary operation on the natural, and then you say, okay, I can define a magma structure on the natural. You can define it on Boole, and here we will have some exercises about how defining a prop structure using AND, for instance. AND is a binary operation from prop to prop to prop, and you can use it to define a magma structure on prop. This you're very well encouraged to do so. And you see, it is not so stupid, Lin, in the sense that, for instance, now that you have defined a magma structure, so you have endowed N with a sum function, you can evaluate this sum of 3 and 2. 3 is an element in N, 2 is an element in N, and it knows that sum 3, 2 works. I've also tried to define a notation for this sum using dagger instead of plus, just to have a new one and not to conflict with the classical one. And you can try to do something like, oh, and now I have a notation. I write eval 3 dagger 2. But it's not happy. And the answer, the error message has to do with synthesized. That is a word that you have already heard this week. So I will say something more about this, but the point that what is going on here is that in order for Lin to be happy with these, something more is needed. It really needs to be automatically able to understand which magma structure this symbol is currently referring to. And at this level is incapable of doing so. That's why we invented, well, not we, the clever people invented type classes. So far, if you want to use this operation, you have to explicitly tell Lin which magma structure you are speaking about. And if you do so, you say, oh, I'm taking the sum that comes from nat magma, then it is happy, is able to sum 3 and 2 being natural numbers. And this, of course, is very much cumbersome. We want to be able to write 3 plus 2, not add 3 plus 2, where plus is the plus. It should be automatic. And clearly here, we are not at this stage. So there is something missing here. We are on the, in a sense, on the good track, but we are not done yet.
So in line 93, you said something about assignment.
On line 93 here.
What is this line doing?
So this line, what is this line doing is saying, I have defined this binary operation, which is magma sum, and I am attaching a notation to this binary operation by saying that dagger is the notation for the binary operation. So that if instead of taking, basically I'm saying instead of typing magma.sum, I can type dagger. The problem that if you just type dagger, Lin still wonders to which term of a magma structure you are referring to, and it is unable to come up with automatically. Okay, and this is certainly not something you don't want to be obliged to instruct Lin about. And we will see that the type classes are precisely made to resolve this issue. Okay, so these are. Let's try just for once. Well, I think. What time do we have? No, I started that. No, okay, no, I'll skip it. Okay, but these you can also do as an exercise. But you can very well, I guess, imagine this will somewhere in the library. Perhaps let me just use the first thing here. If I want to define a monoid structure on n, I need to give myself a 0, and I need to give myself an addition, so I can do not.add. So this is a map. It is a binary operation. So far, sum has no other constraint by being of type x to x to x, and not add is of type x to x to x. It has many other properties, but they're not required here. On the other hand, as soon as you start doing something, it will require things like this, but these will be hopefully in the library. Or not, okay. And then it will be right 0. Yes, you're right. Not even.
Yeah, then you got 2 question marks.
You have to. No, because you need to unfold the.
That's 0. Yeah.
How this is 0 add.
0 add.
This is 0 add.
Yeah.
So why could exact question mark not close that?
Nat.0. Yeah.
It's really not. Did you open that?
No, but I don't think I need.
And then maybe there is like, yeah, okay, yeah,
Underscore.
Okay. We're not far. Okay, this is and then zero sum and the associativity. You can. Okay, so these are just small exercises. You can enjoy them or not. The point is that I'm trying to make you play with different ways of populating structures by using different syntaxes. And likewise here, you can play with monoids and so on. So now I'd like to pass to some metric topology and to play with another structure that has a bit more of mathematical content that I call a space with metric. So for reasons that I hope will become clear at the end of my talk, this is the wrong way of defining metric spaces. But this is not a good reason for not trying it and then playing it a little bit with, and then perhaps trying to see why it is the wrong way of defining metric spaces in Mathlib. Okay, so these I'm defining a space with metric. Okay, so it's a type, and to which I'm giving some property, and then these properties are actually the usual properties you would require for a metric space. You have a distance, or that I call d. I'm required it will be 0 for when x equals x, that if they're different, it is strictly positive, it is symmetric, and it satisfies the triangle inequality.
And it's called a space with metric because metric space is taken, right?
It's called a space with metric because metric space is taken, exactly. I mean, technically, I could have used metric spaces because I'm in a namespace. But I really want to, well, space with metric is sufficiently a stupid name so that you can believe me when I tell you that it's the wrong approach, and it will not stick in your mind. But this is a space that has a metric, in a sense. Okay, so now this is just a structure. Then I can try to say, okay, the real numbers can be endowed with a metric structure. Okay, why not? Let's try to do it. So what is D? I just want to do it coherently with the rest of my. Yes. Okay. So this D is a function. So this is something that should go from R to R to R. So it should be a function that takes two components and gives you distance between these two. And I suggest you use the absolute value of x minus y. Okay, this is a binary function. So far it's happy. So the distance is 0, then is the usual result. Hopefully exact is able to close it. It's not. Yes. Because there are two things. First of all, you have a sub-self, and this is able to close it. Okay, whatever, I can put it together. These okay. Let's try to do it. Yeah. And for the triangle, so the symmetry, I had it here. Perhaps one of the reasons I use it, kept it in this way, is because perhaps you have seen us using this dot dot at the end of something. I don't know if you have or not. I just wanted to discuss this syntax a little bit. So what is ab sub com? Let's hover over it. It takes two explicit arguments. Well, 2 is not a long list, but sometimes it happens that you have functions that have a very long number of variables or arguments. And what you're just trying to tell Lean is, please apply this function to all the reasonable, clever arguments that you need, and don't let me count if there are 17 of them, 12 of them, just one, none of them, and so on. And this is exactly what dot dot does. Okay. In this case, I could also have done these because they were just two. But typing these is lengthy, and you never remember if there are 5 or 6 or whatever, and you just dot dot. Okay. And the triangle inequality, well, it's of course in the library. Okay. So far we have put a real metric. A space with metric structure on the real numbers. Okay, an exercise for you is to try to put a space with metric structure on the natural number. You will see it's painful, but it's doable. It's doable, but painful. Perhaps because, well, I don't say anything. I'll be happy to come along, but it's a fun. It's a fun exercise. Okay, and so now what I'm trying to do now is would like to at least convince you that this is the wrong approach. In which sense is it the wrong approach? I haven't done anything mathematically so far, so it seems hard that I can have done something wrong. But the point is that one is really, once you have a topology, once you have a metric, the natural reflex is try to define a topology out of your metric, and to say, oh, each time I have a metric space, I can try to define a topology out of it. And let's see, it's a bit long, so I haven't commented it. I just want to briefly go through, first of all, the syntax, what we are trying to do, the way we say that if we have a space with metric structure, then we can cook up a topological space, and how to do so. So first of all, what I'm defining here is a topological space structure on every type that has a metric, so that has a space with metric structure. And okay, and of course, as soon as I am here, as you've seen with the other day, and I do what we were doing before, you put your underscore, you wait a second, and then Lean tells you that to define a topological space structure, you have to provide the collection of opens and the 3 properties satisfied by this. Okay, and so this is what I did yesterday, and so here we are. Yeah, thanks. Okay, so what do we want to take as opens? Now, for instance, we want to take all the sets such that there exists a row so that the open ball of reddish-royd contained in S. There's a reasonable definition of the topology induced by a metric. And then indeed, if you put this, then you can prove well that the universal space has this property. So the universal set has these properties, the intersection and the union are satisfied. Okay. So why is it a problem? And why do we need type classes? So one hint at our need for type classes I've already given you was the fact that notations, this dagger notation I've tried to introduce for the operation on the magma was not working. Another one, again with a definition that I've skipped, was about the zero. So you can say, oh, I want to define, where is it? Here. I want to use this notation bold zero for the zero in a has zero thing. Why not? You can do so. But as soon as you try to check whether the natural have a zero, so you define your has zero structure on the natural by using zero, and then you try to look at what zero in N is, it complains. And why is it complaining? Well, because so far, this is just a notation that needs to be enriched in a sense with a term of type nat has zero. And this constant requirement is painful and very distant from mathematical usage. We want to be able to say 0 in R, 0 in Q, 0 in C, without starting all over from scratch. Oh, this is the 0 in C, provided you define on C the addition and the multiplication and so on, so defined. Okay? There must be, in a sense, a canonical way to attach this meaning to this kind of thing. But of course, if I add the name of the term that provides the structure, I get somewhere. But this is really not what I want to do. And another reason, so these are this the notational reason, if you want, and the other reason you will see comes from this topology point. Okay, where am I? Classes, structures, classes. Here. So, what is a class? Well, a class is a structure, just that instead of starting with structure, you write class. But it has the same syntax, the same type theoretical properties. The difference is just internal from the computer science point of view, what Lean records and what Lean registers about these structures. And a class, so the idea of type classes is not the only one. Other type assistants like Rock, they don't use type classes, or at least not in this way, to keep track of hierarchies and automation for deriving properties of some types. But type classes is the way that Lean developers came up with. And the idea is to build a huge database of pairs, structure, and term of this structure. So, for instance, in this database, you would like to record that nat is a magma once and for all, so that you don't have each time to pass explicitly what is the binary operation, and to decide. So, first of all, that magma is a sufficiently important structure to show up in this database, and secondly, that nat is a sufficiently important type so that these definition that we have given of a magma structure needs to be recorded. That's all. So, and the way you do so is, first of all, you write class instead of structure to say, oh, I want in this database that has zero and magma appear as possibilities. And the second thing I want to do is, instead of, you remember we had this definition of this term has zero and of this term that I called not zero, which was this term of has zero n, which was our witness that the natural head were pointed with zero. Now, instead of def, you write instance. Instance is the way of saying, okay, in your database, in the column where has zero shows up, put the term, put a term here. You don't actually need to provide it a name. Lynn will cook up a name for you. You can, and I will do it later on. You can come up with a name, but otherwise you are providing this term. You're putting this term into the database so that each time that Lynn will look for a term of type has 0n, instead of trying to look at somewhat trying a goose chase, we'll go into the database and find this term. And now, indeed, this works. Now you can type 0 in n, and it works. So it has recognized that n, and I do it more explicitly here, and I will try to go through the examples for the dagger. It does recognize that n has an has 0 property, and so that 0 as an has 0 thing in n makes sense. The same thing you can do for bool. And for magma, you do the same. Instead of writing structure, you write class, and then you do your. This is at the very same line I wrote before, so this has not changed. Again, it means this dagger means is a shortcut for the sum binary operation on magma. Then instead of defining the magma structure on n, I'm declaring it as an instance. So not only I'm declaring a term, but I'm also recording this term in my database. And now I can try to evaluate 3 dagger 2 dagger 0. And it is happy. And not only it is happy, it gives me the right answer. It's really true. I mean, if I change it to 21, it's still the right answer. And what is it happening here? So what is happening is that, well, Lynn, first of all, encounters this dagger. Says, okay, dagger makes sense provided the left and the right term are endowed with the magma structure, because dagger only makes sense for magmas. Where is the right, the left and the right hand side? Where do they live? Well, for the left hand side, that's easy. Well, for the left hand side, it's not very easy yet, because this is a dagger of 2 things. And the right hand side is not very easy either, because this is a bold 0 of something. But then it starts again. It says, okay, fine. I need to understand what these 2 things are, because I'm still after a magma structure on something. So the situation at this point is that Lynn has introduced what's called a meta variable, so a variable whose value it is still unknown on a type, because it is looking for the type on the left and on the right that should come with a magma structure. Okay, so for instance, let's say it starts with the right. It will, in this case, start from the left. But let's pretend it starts from the right. You say, okay, this is has 0 stuff on something, and I have no clue what this thing might be. So I still keep it as a variable. I just know as an unknown variable. I just still know that the type that should come with an has 0 here. It must be the very same type that comes with an has magma here. But I still have no clue what it is. Let's try to see if I have more luck on the left hand side. So it goes on the left. So it's okay, this is a dagger of something. So it does the same thing. It says, okay, I should look for a type such that my left and my right hand term here, they both belong to the same type, and moreover, this type has a magma structure in it. Now it looks at 3 and at 21 and says, oh, they're natural numbers. Do I happen to know that the naturals are in magma? And yes, it knows that the naturals are in magma precisely because magma is a class. So it shows up in this huge database of things, and because there is an instance of magma n, so close to this magma list, there is as term this thing. So I say, oh, okay, now I understand what this thing is. This thing is the sum attached to the magma structure on n that you have recalled for me once and for all in this database. So I can compute these 2 things. There's 24, and it is natural. Now I go back to my original problem. My original problem was to understand what this dagger means. And this dagger means, oh, it's the sum inside magma. I didn't know what the type was, 5 minutes ago, but now I know because I've computed the left-hand side, and I know the left-hand side is a natural. So again, the type here must be a natural. So the term that this diagram refers to is the term that has no name that provides a magma structure on N. Oh, great. But then I can also try now to understand what this 0 on the right means, because this 0 must be something that comes from and has 0 structure on what? Well, on natural, because these are the type that came up when solving, unifying this problem. And now it can do it, and it can do everything because it has found this magma N term in the library, and it has also found this has 0n term in the library. Okay, so this is how it works, and this is what allows now us to write this kind of thing. And this is what happens all the time when you write 3 times 5 in the complex numbers. It goes around and it finds the relevant instances that give the complex numbers or whatever a multiplicative structure. Okay, so this seems much nicer. You can then play the same game with the space with metric. Instead of defining it as a structure, you can define it as a class. Then you can add exactly as we did before. You can say, oh, each time. So the way, one thing I try to stress about these classes is that they really need to be used for automation. So if you have in mind, if you still believe that this space with metric is the right thing to do, which will not be, but then you say, okay, I want it automatically. Each time I have a metric structure on a space, I can endow it with a topological space. I don't want to each time say explicitly that since I have a metric structure, I am considering the topology induced by this metric structure. So I want to record and pay attention to the difference, well, to the power of this definition with respect to the previous one. In the previous one, I was just, what was it? Here. I was just defining a term of a magma structure on one specific type, which were the naturals. Here, I'm saying, give me any type. I don't care what type, what this type is. As soon as it has a space with metric structure, I'm going to convince you that this type is a topological space. Okay, so this is much more general. It will hold for every possible type endowed with a metric structure. Okay, and so okay, this is exactly the same code I wrote before. And where are the problems? Well, here are the problems. That they are showing up. Okay, it doesn't matter. Let's try to. So I can tell you immediately. The problem is that if you do so, you will soon find yourself with 2 different topologies on R that actually come from the same metric structure. And this is something that you don't want. And Thomas will explain you how to avoid this trap. But I just wanted to make a concrete example. So suppose, for instance, that you want to prove that the function x goes to x plus 1 is continuous. Well, this is in the library. It's called continuous at right. It's fine. It's in the library. Or you can say that the function from R2 to R2 that swaps the 2 component is continuous. Okay. Well, this is the link. I don't know why I wrote it twice. I can simply erase this. Is the same proof. Okay. So you have these 2 things. And indeed, so this speaks about continuity. So it needs that more R and R times R are endowed with topological structures, and you can synthesize the topological space structure on R, which is this. It's written here: pseudometric space dot uniform space to topological space. So this is really the Mathlib definition. This is where the way the reals are endowed with the topological structure. Now, the problem is that if I now try to, yes, let me move this up so that we can compare the 2 before passing to products. I want to compare the 2. Yes. Now, okay, so on line 285, R is a topological space, and the topological space comes from basically the library. But what I can do here is say, okay, I've just defined before a metric structure on the reals, and I therefore can define an instance of metric space on the real. And what happens is that precisely because of this automation, this automatically provides Lin with a topological space instance on the real, which is a new one. Because what I did before was convincing you that as soon as you have a metric structure, you can derive a topological structure. Now, I've defined here a metric structure on R, and therefore automatically Lin tells, oh, can I find a topological space structure on R? Yes, because I find a metric structure on R, and for every type with a metric structure, I have a topological space. But look at the difference here. The name is pseudometric space dot uniform space to topological space. Here is topometric R, which is the name I gave for this lecture. So these two already seem different. And indeed, if you now try to prove that x goes to x plus 1 is continuous, this fails. And why does it fail? Well, because these, although you don't see it immediately, even hovering over it, you don't see. It just says, well, this has to be a topological space with a continuous addition, then this is continuous. The problem is that this works for, well, this has been proven in the library for the topology on R that comes from its uniform space structure. And what I've done here, I've defined a new topology that so happens I can prove it that it coincides with the previous one, but Lin doesn't know it so far. And so when it tries to apply this lemma to the add one function on the reals, it fails. And this is the same thing I did it before. It's the very well, in a sense, it's a slightly more complicated example, but it's in the same spirit. You can once you have defined what is a metric, a space with metric, you can observe that if you have a product, well, two space with metrics, you can define a space with metric structure on the product. And therefore, in particular, you end up with two different topological space structures on R times R. One, which is the usual one, that comes from the product of topological spaces, and the other one that comes through the path, oh, R is a space with metric, then R times R is a space with metric because I've defined a space with metric structure on the product of two spaces that have this property. And now since R times R is a space with metric, I have a construction that brings that constructs a topological space structures on these. And so I find myself with these is the topological space product real Simons 2025. You can imagine it has been defined for today, which is the one that comes from the construction in the previous file. And so now if you try to prove that the function sending n1, n2 to n2, n1, it doesn't compile anymore. This proof breaks, because this proof is fine provided that these and these space are endowed with the product topology, which is not the case here. It is provably equal, but not definitionally equal. So classes are great. These solve many, many problems, but they can also lead to unexpected errors of this form. And it's hard to understand. Let's try, and I will really finish on this.
Question. So this happened because when you, if I understand correctly, on 336, when you that instance statement, you're kind of overriding something that's already there. Is there a way to know when you do that you're overriding something that's already there? Like, is there a
what I can try is to do synth before, so I can you see the fact if I copy this line before 36, I'm trying to define a topological space on R times R. I can try a synth before declaring this new instance, and I already find something. This it's already a very good indication that probably what I'm doing on the signal line is extremely dangerous. Sorry?
Should be a mistake.
Well, but on the other hand, I might very well from time to time consider the, I don't know, the discrete topology on R times R.
Yeah, but if you put a second instance, why the machine will synthesize all the new ones?
Well, because I can decide locally to disable this one or to something. Yeah. But I agree. It should be at least a warning. It should not be an error. You can, provided you know what you're doing is fine. this is a good sign that something is strange. Okay, and comparing these with these shows you that indeed this is the topological space prod, the usual product topology, whereas this is the topological product that comes from the product with metric space that I provided this product with. Okay, and indeed, and what I wanted to show is that how bad this is, because then you say, okay, I try to rewrite with the continuous prod make. You can imagine with continuous prod make is, and the error message you say, static rewrite failed because I could not find an instance of the pattern in the following expression. You say, well, yes, of course you can. There is N2 and 1. So I don't know, you can try to be more, try to say, okay, let's try first of all to produce my term. This at lets me enter every single thing I want to put. So I need to provide an X, a Y, a Z, a topological space on X, a topological space structure on Y, a topological space on Z, two functions, and then, okay, let's try to go. So I'm taking for the first space is R, the second space is R, the third space is R times R. Then I want a topological space on R, fine. A topological space structure on R, okay. A topological space structure on R times R, okay. Function F, function G. Then the function F is fin X maps to, sorry, fin, what am I doing? No, sorry. What is, so F goes from X to X and G goes from X to Z. Oh, no, everything is R. Okay. Fin X goes to X dot 2. And this is fin X maps to X dot 1.
First one is R press R.
F needs to do, sorry. Both are the identity. I don't know what I'm doing, sorry. I can try to, no, I'm trying to do it too fast. And oh, yes, the first one is R2. This one should be R2, I suppose. Yes. So this X dot 2, this is X dot 1. Then I can take the first implication of these. And then I say, okay, really, it is the same thing. Continuous fun, X goes from X dot to X2. So I apply this, and it fails. And now it really fails with a nice problem. But now you somehow see the problem. Well, if you really look into the details, because it tells you that it cannot unify the conclusion of these applies. You see, here I had underscored, and these underscores were, okay, come on, don't make me write down what the topology on R times R, what the topology on R, what the topology on R is. Come up by yourself on these structures. And here you see the problem. It tells you, oh, but this is the topological space product on something, whereas I am looking for the topological space prod on something. So this is telling you I'm able to understand, to prove for you that endowed with the product topology, this would be continuous, but you're requiring me to prove it for this crazy topology coming from this stuff. But you have to really start digging into the details of this. So of course it's doable, but it is painful, and this is not the way it should be done. Okay, I'll stop here, and Thomas will take up from here. Yeah, perhaps we take, I don't know what time you want to resume. I'll let to the organizers.
3.
At 3. We resume at 3 after tea, coffee, cookies, fruit, whatever. Thank you.
Thank you.